All right, now you should be able to hear me, yeah? I'm sorry. Can you hear me? Okay, sorry. My OBS somehow defaulted to some other microphone. I have like 3 microphones on this computer. Anyway, what I was saying is that I have some extra slides related to the network project that some of you may be interested in looking at. It talks about VPNs and how you could do some VPN even on our simulated network. So I know that a lot of you are using VPNs. So if you want, you can take a look at how would it go if you wanted to do so for example, a VPN inside a simulated network. So you may want to take a look at that. But I don't have time to go to talk about it because we have a long lecture today. I'd rather just dive right in onto the topic of today, which is algorithms and programming, which is the sort of the core of computers in a way, in the core of computer science. And I know that it's some of the material that it's really complicated. It's complicated to get into. Once you're there, it becomes a little easier. But getting into this is really, I know it's a very steep slope here. So hopefully I'll be able to smooth this out for you a little bit today. So let's. I'm going to talk about something that I call scars, which is the core of algorithms. It's sequencing, conditionals, alternatives, repetitions, and state. And if you understand these 5 things, I think you'll be very well equipped to be able to express algorithms, at least the ones that you understand. So let me go into this. So suppose, for example, let's go back to the average. So you want to compute the average of n numbers, and you all know how to do this. You know, this is a problem that everybody understands. You understand. You all know how to teach it to younger siblings and cousins. Something like, add the n numbers and then divide by n. You give an example. For example, if it's 3, then just add the 3 numbers and divide by 3. And that should do it. So we're using language, the English language to express what we want to do, and that's fine. But now suppose that I tell you, okay, now teach it to a kid who only speaks German. All right, so how would you teach the average to a kid who only speaks German? And I'm assuming that none of you speaks German, because if you speak German, that would be easy. But if you don't speak German, that would be a problem, right? Like, okay. So maybe in the particular case of average, maybe you will get helped by the fact that the average is a mathematical concept, and that we can rely on the existence of a universal mathematical language that all the kids sort of understand. So you might be able to, with numbers and some arrows, you might be able to get your message across. Maybe, here's an example, this means this and that means that, and now let me generalize a little bit more. Maybe. Okay, so here you would be making, use of some the fact that the kid may know what numbers are, and the plus sign and the equal sign, and plus the arrows that are kind of an intuitive language for everybody. Maybe. But now suppose another one. For example, sort a set of n numbers. To a kid who only speaks German, right, or to a computer. This is a little harder because this is not really mathematics, right? There's a little bit of mathematics you have to compare, but that's about it. But it's nothing like sums or anything. It's just pure sort of steps and sequencing and procedural things. And there's no mathematics does not have a language for this. So we cannot use the language of mathematics. And if we cannot use English, then that would be a big problem. So we need a language, right? And the point that I want to let you know is that understanding the problem is one thing, and your understanding is yours alone. It's inside your head. Everybody understands problems in slightly different ways, and that's fine. But that's only part of the issue here. The other part is that we need to express the solutions. We need to externalize the solutions, either to a person or to a computer. In this case, to a computer. So in order to communicate it, we need a language, and mathematics does not give us that language. It's not enough to know mathematics in order to be able to express algorithms. Okay, so of course, if the target is a person, again, we can kind of make do with English and some semi-formal mathematics, but if the target is a computer, then what we really need is a complete artificial language that the computer can understand. And in order for the computer to understand, we need to speak that artificial language, and the computer needs to speak that artificial language, and then we'll be able to communicate the, what we want to say, the procedural steps. What are these languages? What is it that computers can understand? So they are artificial. Computers in general, especially for writing programs, they don't really understand natural language. People have tried to use natural language to program, and the result is always very disappointing. It just doesn't work. And the reason is that programs and algorithms require a certain kind of language that it's just better to have a special language for those kinds of things than to try to use English or natural languages that are not designed to be so procedural. So these languages for computational solutions need to capture the properties of algorithms. So it's important to understand what are the properties of algorithms. What is this, right? Yes, it's sort of a sequence of steps. So what is it that we do when we are, expressing algorithms? This is where scars come. So every language for algorithms basically boils down to these 5 things. Sequencing of steps, right? So do this first, then do that next, then do that, etc. So sequencing is important. Conditionals, what are these conditionals? Conditionals is testing if something is true. Is this true? If it's true, then do this, otherwise do that. Okay, so these are the conditionals. Another one is alternative. So you look at the value of something, and then depending on the value, you do something. For example, I'm looking at the chair, right? I'm looking at chairs here in this virtual world. If the chair is red, then I do something. If the chair is yellow, then I do something else. If the chair is blue, so those are alternatives. This is something that we do in algorithms too. Another thing that we do in algorithms is repetitions. We need to repeat things a lot. You've probably already seen that, and I'm going to stress where this comes from. But basically, we need to repeat this something over and over again, right? Or many times, or until something is true. And finally, the last letter in SCARS is S of state. What is state? So state is remembering things that are important during the computation. So basically, is things that are so important that we hold them in memory, in our working memory. The thing on the left, we will hold them in memory because they are important for the ensuing computation. And not only that, they may change as the computation unfolds. So they have a value at some point, and then you do something and you need to update that value, okay, at some point in time. So this is called state. It's remembering and updating the values of certain things throughout the computation task, okay? SCARs are the 5 principles of algorithmic languages. Okay, if we have any language that is supposed to express algorithms, needs to be able to express these 5 things, and these 5 things alone. Basically, there's not much more that we need to express other than these 5 things. So let me explain how this goes, looking into an algorithm that we're using here in the lecture, which is the max, right? So the max of 8 numbers or something like that. So here's the algorithm that I wrote in the previous lecture last week. It was something like this. So where is sequencing? Well, sequencing is in the fact that we read this from top to bottom, right? So we start in the first line, and then we go to the next line, and then to go to the next line, etc., 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 right? So in principle, it's from top to bottom. This is kind of broken when we have the jumps and the conditionals. It may not be so linear. So sometimes, for example, if you test something here, then you go to the next line. But if it's false, then you go 2 lines. You go to that part over there. It's not sort of a linear. Skip something over here. So, but in general, sequencing goes from top to the bottom. All right. So that's the basic principle. Conditionals. Where are the conditionals here? Well, the conditions are on all these tests are conditionals, right? So whenever we have a test, and I have been marking it as test just to remind ourselves about what is this. Well, it's a test, okay? So a test, and I'm just highlighting this final one, but all of the other ones are tests too. So this final one is basically consists of all of the conditionals consist of 3 parts. They consist of the test itself. So we test if something is true. So in this case, if we test if counter is 0, right? And then there's a what to do when the test is true and what to do when the test is false, right? So conditionals are three things: are the condition itself, the predicate that we test, is this true? And then the next one is what to do if this is true, and the other one is what to do if this is false. Okay, so these are the conditionals. We also have this in normal language, right? You know, bring whole milk. If you find whole milk in the shelves, bring whole milk. Otherwise, bring 2% milk, right? That's sort of the conditionals that we also use in natural language. Alternatives in the max, we don't have alternatives. I have another algorithm that I want to cover today that has some alternatives. I'll explain. But basically, alternatives is if you look at something in memory and then you say, depending on the value, you may do several things, right? Depending on its value. Repetition. So we've seen this, right? So repetitions is that the idea that there is a block of our algorithm that in certain circumstances we want to repeat it many times. So this is when we have like go back to some place before, right? So go back to before. Basically do this again. So repetitions are an important component of algorithms, very important, because a lot of algorithms they usually use work on many numbers or many texts or something like that, many, right? So you kind of have to do things over and over and over again. That's what computers do for us, right? So repetitions is a super important point that we need to have this concept of repetitions in our algorithmic languages. Okay. And finally, state. So this is the part that may be a little hard to grasp at first, but the idea, we have that working memory of the computer. And the idea is that, we also have the registers, and we can do a lot. Even with just 3 registers, we can do a lot. But the best idea is that, if it's something that it's important for what you are doing, then don't just have it in the registers. Keep it in some place safe in memory, because the registers, there's all sorts of things that happen to the registers while you compute and do some operations that can actually destroy things in there, and then you don't remember what it is anymore. So the memory is there to hold the important things. So in an algorithm like this, what is it that is state? Well, it's the things that we need to remember that are important through the computation. So for example, if this is the max, then the current max, the number that we have, the maximum number that we have seen so far, that is something important to remember, because we're going to have to compare that current maximum with additional numbers that we are going to see, right? So the maximum is definitely something that we need to keep in memory. Another thing in this particular case of this algorithm is that we want to do this 8 times, right? So we need to have some sort of a counter that decrements as we do this several times. So we need to have a counter in memory that starts at 8 and every time is decremented. So this is also in memory. So in this case, it would be just the max and the counter in this particular case. And then as you see, both the max and the counter may change as the algorithm unfolds. So for example, the max changes here when we find a number that's actually greater than our current max. Then we replace the value, we just update the value of max with a new value, right? So it changes value over the execution of this algorithm. And the counter also changes as we go along. So counter always decrements every time that we have we process one number, and it decrements the counter, so that then we can test it if we arrived at 0, right? So this is what state is. State is things that are important for our algorithm that we need to remember throughout the algorithm. And in order to do that, we, in the pseudocode, we give them names that make sense for us, right? And so, for example, the max is the max, the counter is the counter. It's good to have good names, so we can remember what is it that those names mean. So, for example, if you did the quiz on Tuesday, I had some algorithms in there where I kind of obfuscated this, one of these states names, right? I called it thing, because if I had called it, min, you would immediately know what that was about, right? Or sum, you would immediately know that was the min and the sum. So I on purpose changed the name to thing, so that you wouldn't know by the word that I chose what is it that the algorithm did. But in principle, when you're writing these pseudocodes, it's really important that you actually find good words, because they help you remember what is it that you are doing, right? So max and counter are good words. And again, state is something that you want to remember. You retrieve it at points in the computation. So you go back to memory and bring it to the registers for doing something, at the registers. And then you change. You can also change. So you change as the computation unfolds. Okay. So state is a really, really important part of algorithms. So to recap, all languages for computation algorithms need to be able to do these 5 things: sequencing, conditionals, alternatives, repetitions, and state. And that's pretty much it. All right. If you understand these 5 things, you'll be equipped to write algorithms. There's not much more than this. Okay. So let me start getting now. Let me show you another algorithm, which is part of your homework of this week. Which is linear search. Is a simplified version of your homework exercise. So in this one, you just search one number, just search once. So so the input is 12 random numbers in memory, the locations 0 through 11, and you have one number, not many. Okay, you have just one number, and you want to find out if that number is in those 12 numbers that are in memory. Okay, and then the output is 0 if the number is there, and it's I'm sorry, 0 if the number is not there, and 1 if the number is found. Okay, so I'm going to let you think for a little bit, just for a minute. I'll be silent, and you guys pull up some, I don't know, paper or a notepad or something, and try to write this before I show you the algorithm. Just think a little bit about how you do it. And just for inspiration, let me just put this one here, just for inspiration. Okay, of course it's going to be a different algorithm. So remember, let's try to do the linear search algorithm with just one number to search. Okay, so I hope that you tried, because it's always good to struggle, so to be prepared. So let me just show you how the algorithm looks like, and I'll step you through it. So we want to output 0 if it's not present, and 1 if it is. So what are the important things that we need to remember here? That's we need to sweep, and I'm starting with linear search because linear search is very, very simple, right? So we have a number, we have some set of numbers in memory, an order, and we start with the first. We compare the number with the first one. If it's equal, then we found it. If it's not equal, then we move to the second one, we compare it, etc., until we reach the end of 12 numbers, right? So that's linear search. Is super, super simple. So one thing that we will need to remember is the index, right? The index is the location that we are comparing our number to at any particular point in time. So we start with the index at 0, right? The index is like when we have a set of numbers, each number is in a position, right? So it's the first one is in position 0, the second one is in location 1, 2, 3, etc. So the index is this number that says in what position am I looking at, right? So we first start at position 0. And then we may also want to have, this is not necessary, if you go straight to the machine level code, you might not even have this found thing, but I find this is kind of useful to have, whether we found it or not, right? So we have something in memory that says, okay, did we find it or not? And then at the end, we print that location in memory, all right? So that's the idea. So at the end result, in the end, the result is in found. Found is going to be 0 or 1, and we just print found. It's super easy, okay? So what's all of this thing in the middle? So what we do? So here's what the first thing that we need to do is a test, right? We check if the value of the location at index, whatever the index is, it starts with 1, and then we'll increment it, equals to n or not, right? If it is, the value of that location is n, then we found it, right? So we say, okay, so now we're going to change the value of found to 1. We're going to put 1 in the location of found, and that's it, we're done, we found it. Okay, we go to the end. We just retrieve again the found thing from memory and we print it out. All right. If it's not, so if it's not the same, then what we do, we increment the index, right? We move to the next spot. And then now we need to test, did we reach 12? Are we done? Like, did we sweep everything? So we test if the index is 12, and if the index is 12, then we didn't find anything. We go to the end, and again, we retrieve the found, and in that case, the found is going to be 0 because we never changed it, right? We reached location 12 without, it means that nothing has been found. So we retrieve found that has 0 and print it out. Otherwise, if it's not 12, then we go back, we do it again, right? We repeat this, we go back to sweep, and we test again the value that we have of the number with the current index that has been incremented, right? And etc. All right? Does this make sense? Any questions here? No? Pretty clear? Okay, I'm trying to see if I can, in OBS, get the chat bar of Twitch, but I don't find a way of getting it back for some reason. I don't know where it went. Okay, so let me know, even if I continue here, if you have any questions about this, just type it in chat. Okay, so this is the algorithm for checking whether one given number is present in a set of 12 random numbers, right? So your homework is almost like this, but not exactly. So your homework is that. Oh, by the way, before I even say that, let me just point this out again. I want to stress this out. If you have these 5 concepts of the scars, okay, you are able to so where are the states, right? What's the state? The states are the 12 numbers in memory. So those are in the location 0 through 11. That's part of the state. The n is also part of the state. So the number that we want to search is an important thing, is part of the state. We want to remember that, throughout the computation. We don't want to lose what was that number that we are looking for. And the index and the found is also part of the state. So all of these are part of the state. And again, this state are things that we go retrieve it. We may change it or not. Some things change, some things don't change, and that's okay. So all of that is part of the state. Here, the sequencing, again, start from top to bottom. That's the default. Conditionals, there are conditionals. So here's a conditional, here's another conditional. Here's repetitions, right, when we go back to sweep. So all of this, as I said, as long as you understand the 5 fundamental concepts of expressing algorithms, the scars, you should be able to just limit yourself to that language of those 5 things. Sequencing, conditionals, alternatives that I haven't shown yet, repetitions, and state. So for your homework, it's almost like that, but the input is now a sequence of numbers entered by the user, right? So it's not just one. Now you have to, the specifications that you keep on a loop, you stay on an infinite loop searching for numbers that are inputted by the user. So this should be, and then, the output is 0 when n is present and 1 when it is, right? It's not just a one thing. It's for every number, you have to output 0 or 1. So how do you modify this? What additional steps, if any? What additional conditionals, if any? What additional repetitions, if any? What additional state, if any? That's the things that, given the base algorithm that I gave you here, which is almost, the final thing, what else do we need to add here that does this extra thing that now it's not just one, it's many, right? And I'm not going to give you the solution. I'm just going to just zoom in and just zoom out and tell you that the solution is something like this, okay? That you need to put something here and you need to put something there extra, all right? But it's obfuscated so that I don't give you the entire solution. But the solution, you know, you just need to think, you know, what else do you need to do here to be able to cope with the fact that now it's a sequence of numbers, not just one. All right? Does that make sense? Okay, so now let me go to another algorithm. I'm going to present another algorithm which is not in your homework. This is called jump search, and it's a third search algorithm that is sort of middle ground between a linear search and binary search. And I'll explain how it works, okay? It's not part of the homework project, but it will give you a lot of cues about how to do binary search, the binary search part of the homework. So first, I need to explain to you what the algorithm is about, right? You need to understand what the algorithm is about even before we even put it in pseudocode. You need to understand what it's what jump search does. So let me try to explain with pictures. So suppose that you have a bunch of numbers that are unsorted, and you have a number that you want to search, like 21. All right. So what do we do? How does this algorithm work? The first thing that you do, just like in binary search, by the way, is to sort the numbers. So first we need to sort the numbers. And for that, we use algorithms that we already know, like bubble sort, for example, or another one. So we sort the numbers. Now, this is step one of jump search. So now, after the numbers are sorted, here's what we're going to do. We're going to do this. So the second step is compare the number n with the value at location 0. So we start by the 0, and we're going to these are some alternatives, right? The things that can happen, they're equal, the number is less than the value at that location, or the number is greater than the value at that location. Those are the three alternatives that can happen when you compare these two numbers, right? So here's what this algorithm does. If they're equal, then great, we found it, right? We're done. If the number is less than the value at this location 0, then it's because the number doesn't exist for sure, right? So if we're looking for example, for the number 1, and if the sequence starts at 2, since the numbers are ordered already, then it's guaranteed. If the first one is greater than the number that we're looking, then that number is not here for sure, because all the other numbers to the right are going to be greater anyway. Okay, so that's the other thing. At location 0, we have to do a special case, which is this one, that if the value is less than it's not, then the first one, then for sure it's not here. And then this is the jump search part of the algorithm. If the value is greater than the value at location 0, then here's what we're going to do. It's going to jump. We're going to skip to location 4. Okay? We're going to skip a big step, like to location 4, which is this one. So let's do that. We're going to skip at location 4. So now we're going to go on repetitions. We're going to do something many times in principle, unless we find the number, in the meantime. So here's what we're going to do. We're going to compare the number with the value at the current location. Okay, so we're going to compare, 21 with 17. And now again, three things can happen. Either they're equal, either the number is less than the number at this location, or the number is greater than the number at this location. Those are the three only possibilities. So if the number is equal, we found it. Okay, we're done. If the number is less than the value at this position, it means that we jumped too much, right? We jumped over. So what that means is that we have to go back again. So this is what the algorithm is doing. This is the specification of the algorithm. So this is what's called jump search, because it keeps jumping. So it jumps back, skips back 4, and then does a linear search. Okay, then does the regular linear search that I just explained before in the next three locations. However, if the number is still greater than the value at this location, then we skip another 4, right? So we just jump ahead, which is the case here. So we jump again, all right? And then do it again. So we go back to see again. Is it equal? No, it's not equal in this case. Is it less than the value at? I'm sorry, this should not be 0. This not location 0. This should be at the current location. Okay, I'll fix the slides. Should be at the current location. Skip back. So that's what we did. We skipped back. And now we're going to do a linear search from here, right? Because we know that the number is somewhere between 17 and 34. If it exists, it's in this block of numbers. We still don't know if it exists or not. But if it exists, we at least now know that it's between this number and this number. Okay? So now this part boils down to just linear search. So we're going to go back again. We don't need to compare with this number because we already compared it before and we found out that the number is actually greater, so we don't need to compare it. So we just need to move to this one, right? Is this the same? Is this equal? Now we just actually need to test for equality. We don't need to test whether it's greater or not, according to the algorithm. Okay, there are small variations of the algorithm, but the algorithm says linear search. So linear search is just check whether it's equal. Now it's not equal. We move to the next. It's equal. We found it. Okay, so now we're done. So this is how it works. Let me show you how it works if it's a number that's not there. So if, for example, number 3. Again, you start the step 2. We compared location 0. It's greater, so it means that you're going to jump. You skip to that location number 4. Now we're going to compare, and in this case, 3 is less than 17. So it means that we jumped too much. So that the number, if it exists, is in between the position 0 and position 4. All right, so we're going to go back. And now we're going to compare the linear search. Is this equal? No. Is this equal? No. Is this equal? No. And now, we only needed to search in this block, not the entire thing. So now we search those 3 locations and we didn't find it, then the number is not here, right? So this is how skip search works, or jump search. It works by first doing these big jumps, by 4. It could be another number, but for the purposes of our computing machine, 4 is a good number. So you skip by 4, and if you skip too much, then you go back and then you do a linear search. All right, everybody understood how jump search is supposed to work? Okay, so as I told you the other time, the first step of algorithms is understanding how the algorithm works. Okay, and that is inside your head. I cannot really check. It's inside your head. Every one of you is going to have a slightly different visualization, kind of understanding of how the algorithm works, but it's inside your head, and that's great. Okay. So now let's try to write this in pseudocode. Okay. So how are we going to write this in pseudocode? What's the pseudocode of this algorithm? So I'm going to present it to you, and I'm going to go very slowly through the major parts of it. So here's the input. It's 12 random numbers in memory, location 0 through 11, and then one number that is the number to be searched, right? And the output is 0 if n is not present, and 1 if the number is present. Okay. So what's step number 1? Sort the numbers. And by the way, because bubble sort is something that you guys are going to do, you can just say sort the numbers using bubble sort. You don't need to, copy paste bubble sort pseudocode in here. Just say sort the numbers using bubble sort. That's perfectly fine for the purposes of defining algorithms. If you already have an algorithm defined elsewhere that does whatever you need to do in that step, you just say, okay, do that I defined elsewhere. All right. So you say sort the numbers using bubble sort. Great. And in this case, we're going to need some extra state, and I'll explain. We're going to need the index. We're going to also want the found state, whether it's been found or not. And we're going to have a marker that I explain what this marker is a little bit here when I explain the algorithm. So here's what we're going to do. So as I say, the first step number 1, this step is to compare the number with the value at location 0. All right, so we need to do this in pseudocode, right? So it's this part over here. This part is the part that does that. That's comparing with location 0. So index here is the location, right? So we're at location index 0. So we compare n with the value at index at 0. If n equals the value, then we found it, right? We say found gets 1, and we're done. Go to the end. All right. If n is less than the value, then in this case, because we're comparing the very first location, then if it's less, it's because it doesn't exist for sure. So we just say, okay, go to the end, and found is 0 anyway. We don't need to update found. If n is greater than the value, then this is when we skip. So we just say, okay, so now index gets the number 4. So we put 4 on the index. So Bevan has a question. Does this program list the 12 numbers from smallest to greatest? No. So this program, in principle, not. But the first very step is to sort them, right? So this is the part where I was saying that you can just, in the algorithm for the jump search, you can refer to an algorithm for sorting. Okay, so you just say sort the numbers. All right, and as long as you have done this algorithm somewhere else in your homework, sort the numbers, you don't need to repeat it here. All right, does that answer your question, Bevan? Emily has a question too. Are there several correct ways for writing the pseudocode, or is there only one correct way? Emily, excellent question. So this is, let me repeat because it's an excellent question. Are there several correct ways for writing the pseudocode, or is there only one correct way? There are several correct ways, okay? So this is, again, pseudocode is language, and even code is language. And what that means is that in language, there is always multiple ways of saying the same thing. Okay, and so there's not just one correct way. There's many correct ways, and there are many incorrect ways too. So you can have smaller, you can end up with pseudocodes that are slightly different, and they, as long as they do the right things and they end up with the right things, that's fine too. Okay, there's not just one correct solution. And that's why sometimes it's very difficult to explain and to teach this, because the model that you have in your head, the model of the problem that you build in your head, may not be exactly the same model that I have in my head, right? And so when I express my solution, I express my solution. I don't express your solution, but your solution may be correct too. It's just a different way of looking at the problem, a different angle, and that's perfectly fine, right? So this is the first part, and so we, if it's not there, then we jump to position 4, and then we'll go on a sort of a loop step over here. So here's what we're going to do. We're going to compare the number with the value at the current index, which started by being 4, but it may be updated as we go along. If it's equal, then we found it. Go to the end. If it's less than the value, so if the number is less than the value that you're looking at, then it means that we went too far, right? So we need to jump back. But in that case, this is important. It's important to remember where we were, right? This is where marker comes to play, because now we need to remember where we were in the position, because now when we're going to do the linear search, we only need to search linearly until that place where we were. Okay, we don't want to continue to search until the end of the set. We know that the number, if it exists, it's in this block. And how do we know this block? Well, it's 4 minus the place where we are until the place where we are. So we need to remember where we are before we update the index, right? So we first remember, oh my God, this is the other way around. The marker gets the index. I'm so dyslexic, I swear to God. This is the flipped around. The marker gets the index. Can I change this? Let me see. All right, maybe. Here, the marker gets the index. And I put this bigger. No, whatever. Okay, so the marker gets the index. That's the important thing. That's what should have been here. Oh, man. There. Okay. I'll correct it. So before we update the index, with -4, we need to remember where the index was. So that's why this marker comes into play. And then we update the index, right? We subtract 4, we go back 4, and then we go do it again. Right? We go, no, actually, don't do it again. We go to the sweep. Now we do the linear search, right? So the sweep, it's this block of pseudocode over here that's pretty much copy paste of what I just did before, linear search. Okay, I almost could say linear search. But the reason why I don't say linear search is because I just wanted to tell you where the marker comes in as being used here, because now it's not up to position 12, it's not only to position marker. So anyway, so this is what happens when n is less than the value. When n is greater than the value, then we jump, we put the index plus 4, and then we do it again, right? And so that's basically sort of how it goes until it, you know what, I should probably test also here. Here's one thing that is incomplete. Homework for you guys if you want to complete what I've done here. I need to test if I'm past the 12 positions, right? So I need to test the index that it doesn't go above 12. I forgot to put this here. Okay, but so once we get, if we find something over here, then this part is very similar to, let me go. Can I close this thing? No. There. Okay, so this part over here is very similar to, it's almost the same as before, the linear search. But now the important thing is that we only test until the marker, right? So we only test the index. When the index gets to the marker, then we are sure that we didn't find it. And so we can go to the end, we didn't find it. All right? So that's, and then the end is that the result is infound, you just need to print it out. Okay? Any questions about the jump search? Okay, so as I said, this is almost as the linear search that I presented before. The difference is that before I had this 12, hard-coded 12 over here, and now it's not 12. It's that marker over there that I have it wrong here. Marker goes to, the index goes to the marker. Okay, so now pseudocode, I hope that you guys can do the pseudocode parts. It's not, it's not that hard as long as you understand these 5 fundamental concepts of sequencing, conditionals, alternatives, repetitions, and state. Those are the 5 fundamental components of an algorithmic language. Now let's see, how can we go from pseudocode to actual code? Okay, this is yet another translation. Okay, so the first translation is from our understanding in memory to pseudocode. And the second translation is from the pseudocode to the actual code in whatever programming language you need to map this to. In this case, it's the the language that we are using here. So first, let me explain how the scarce concepts map into this language. So this language embodies, because all algorithmic languages, all programming languages have to embody these 5 concepts. They may have more things. In fact, the programming languages have a lot more things than the algorithmic languages. The algorithmic languages is really just, those 5 things, nothing else. Programming languages have usually a lot of other extra concepts. But they all have the sequencing, the scarce concept. So the sequencing, well, it's top to bottom as expected, unless there are jumps. So sequencing is there. You know how to read. We start in line on the top and we go down. Conditionals, where do we get conditionals? Well, conditionals, I actually added, if you notice, a better instruction for conditionals, which is the compare, right? So the compare compares some memory locations, and then puts a value in register 0 that you have to check. So if its value is 0, it's because the first location is greater than the second one. If the value is 1, it's the opposite. And if the value is 2, it's because they are equal. All right, so read the specifications of these new instructions that I added to the machine. So compare, and I'll explain a little bit more where does this compare come from. But it's an additional instruction that I added to our machine language. So compare is how do you do conditionals is with compares. All right. Repetitions, here they are. Okay, so it's these jumps back, especially the jumps back. The jumps forward are not really repetitions. The jump back are the repetitions, right? You did something, now you're doing it again. So you're repeating it again. State. So the state is kind of hard to it doesn't have names as such because it's a very low level language. But what I told you that you're going to use memory locations to hold important values. And I even told you, write it down, either in the comments or in the paper. Just write it down. What is it that you are storing in, for example, location 15? Or is it that you are storing in location 14, right? Write it down. Those things mean things. And this is exactly how we're going to map the things that I wrote in the algorithm to the program. So in this case, I'm saying that location 15 has the current max, okay? And location 14 has the number that was entered by the user. Okay, so this is the max. It does, I could have put also an index. It would be important to have in the memory, but I'm being able to get away with having the index always in the registers because this is such a small program. But this is not something that you should do for larger programs to keep important things just in the registers because you're going to need all the registers. So it's important that you put the important pieces of states, put them in memory. So let's try to write this algorithm in our machine language. So this is the linear search, the simplified version of linear search. How do we write this in machine language? So this is the pseudocode, right? And again, here's all the things that we need, sequencing, states, conditionals, repetitions, all that stuff are here. So how are we going to translate from this semi-formal language into the very formal language of our computing machine? So I'm going to just give you the solution, but I'm going to walk you very slowly through this. So the input, what are we going to do about the input? So the input it's important, it's part of the state, right? So the numbers the set of numbers and the number that we are searching for are important parts of the state. So let's make sure that we put everything in memory. So in this case, again, there's a new instruction that the machine has, which is random, and then some number, which means that fill out the 12, the 12 first locations of memory with random numbers. All right, that's what this means. So they are from 0 to 11. Okay, this is what they are. They are in memory. And then we read the number from the user. And now what I'm saying from here on, when you're dealing with more complicated algorithms, always store important things in memory. Don't leave them in the registers because you're going to need the registers to do all sorted operations, and then things are going to be overwritten and you'll never recover them again. So let's make sure that to put our n, I'm just saying on location 15. Okay, so location 15 is going to have the number that the user input. All right. And furthermore, even though I don't have a way to express it in the language, I can put a comment in here that says that the index is going to be at location 14 and the found is going to be at location 13. All right, so those are the important state of my algorithm, and I'm going to put it in locations 15, 14, and 13. The input number, the input number, the index, and the found number, whether 0 or 1, that we're going to print out at the end. All right. So the language doesn't let me tell this, but it's important to me, and it's important for me to express this to you. So I'm putting here in comments. All right, just to remind myself. So then what are we going to do? So we are definitely going to go on a loop over here, right? So this is a loop that I call sweep. I'm giving, again, I use comments, to remind myself what is it that I'm doing. So this is the sweep loop of my algorithm. So what are we going to do here? Well, we're going to compare the value of the location at index with the number n. So we need to get both the value of the location at the index and the number n. We need to get them in and compare them, right? So how are we going to compare them? I am going to compare them with the compare star. So this is where I'm going, okay? I'm skipping 2 lines, but this is where I'm going. And compare star is a version of compare that compares the values at the locations that are stored in these registers, okay? So this is the indirect addressing, right? So it's the registers now have not they have values that represent locations in memory. Okay, so for that, for me to do that comparison, what I'm going to do is that I'm going to fetch 14, which is the index, to register 1. And again, the index is an address, right? The index, that's why I'm doing this. So I'm going to fetch the index to register 1, and I'm going to set register 2 to 15, which is the memory location that has the n. All right? So now I'm comparing apples to apples. I'm comparing locations. I'm comparing the location 15 with the location that is embodied in the value of the index. Okay? And so the way that compare works is as if they are equal, then the number 2 is placed on register 0. Okay, that's the specification of the compare operation in this machine. So if they are equal, then we would like to know, because then we're done. Okay, we just say, okay, we found it, great. So if they are equal, we're done. So now we need to check if the register 0 has a 2 in there or not. If it does not have a 2, then it's because they are not equal. So so to check if it's a 2 or not, there's different ways of doing this. One way is by dividing by 2. So if you divide by 2, so again, the value in our 0, it's either 0, 1, or 2. Okay? So if you divide by 2, the 0 or the 1, you're going to get 0. If you divide 2 by 2, then it's the only alternative that you're going to get the 1. Okay? So if you divide and you get the 1, then it's because they were equal. All right? So this is what we're doing here. We're setting this 2, dividing our 2 by 2, and then if it's 0, it's because they are not equal. Okay, so if they are not equal, we're going to jump ahead. But if they are equal, then we found it, right? So if we found it, what are we going to do? Well, we're going to put a 1 in location 13, right? So location 13 is the found flag, right? So we're going to put a 1 there. Okay, so here's how we do it. We put 1 in the register, and then we store that register location 13, and we're done, right? We jump to the end. We're done because we found it in the very first thing. If we didn't find it, however, we go to line 14, which is the next, which is this one over here. Okay, so we didn't find it. What we need to go? We need to do this thing over here. So we need to increment the index, and then we need to test if the index is 12 or not, if did we reach the end or not. Otherwise, we go back to the sweep. If you didn't reach the end, we go back to the sweep. So this is the part that starts here. So we need to go grab the index that's in location 14. Okay, so let's put it in some register. We need to increment it, right? We increment it, and then we put it back again, even before comparing anything. Just make sure that it's saved back in memory. So we fetched it, we incremented it, and we store it back in memory. And now we're going to check if it reached 12 or not. All right. So how are we going to do the same trick? So this is what I'm going to do. If we divide by 12, if the end is 0, it's because we didn't reach 12 yet. If the result is 1, then it's because we reached 12. Okay, so by dividing by 12, so if it's 0, then it's not 12, then we go back to sweep. Maybe we go back here again. If we reach 12, then we're out of luck. We didn't find anything. We just continue here. We fetch the found flag, which is in whatever it is, the value at location 13, and we just write it out. That's it. Okay? Does that make sense? Any questions? I will come back to this linear search algorithm in a little bit, but let me move on. So I'm talking about language, and language is a really important part of computer science for many reasons. It's sort of a big attraction or detraction. Some people hate it, some people love it, but the way that we program computers is with these programming languages. These very formal, unforgiving languages that if you have something wrong, the computer will tell you in the worst possible way that you did something wrong, or maybe it will not tell you, but it will not work, and then you're kind of stuck. So what are these programming languages? There's thousands of programming languages, not just one. Okay, there's thousands. And they're roughly, to some approximation, you can divide them into two groups. There's the assembly languages where our machine is right now. They're the ones that are very close to the operation of the machine. And then there are the structured or high level, what's called high level languages that are a little bit more removed from the machine. And within those, there's many different kinds of families of languages. As I said, there's thousands of programming languages. So our machine language, and on purpose, I designed a language for you for this class that is very, very close to the machine, so that it's a class about how computers work. I think it's important that at the bottom how the things work at the bottom. Okay, and it can be very confusing, but on the other hand, it can be very enlightening because you see everything that is working. There's not magic. There's no magic in here. It's very clear what is it that's being done in the registers, in the memory, the jumps and all of that stuff. So there's no magic. And the higher level languages, sometimes they're a little magic because without understanding what's going on at the lower level, there's a lot of kind of faith-based learning that you kind of need to accept things without really understanding what they mean at the level of the computer. So that's why, on purpose, I designed the language for this class that was very, very low level so that you really operate the machine. But that's not true in general. The programming languages most programmers use are high-level languages that make a lot of things much, much easier. Um, so assembly language at low level is primarily designed for the control of the machine, control the operation of the computing machine. And you can really see, it's about the registers, it's about fetching things in the memory, storing things from memory, jumping here, jumping there. It's very kind of operational. The structured high-level languages are things that are languages that have been designed basically from the 60s onward, from 1960s onward, when people started to realize that certain things that we do in the low-level languages are a little, shall we say, repetitive, and they're harder than what they need to be when we think sort of at a higher level. And so people started designing languages on top of languages, right? Things that you can do are languages, instructions that are sort of higher level, that they encapsulate higher level concepts than just the operation of the machine. And so these are designed first and foremost to capture the scarce concepts in a way that makes more sense for people, right? Not for computers, because computers don't really care, but they care about the operation. But for people, it's important for us to be able to express things a little better than just so low level. So here's an example, a little preview of what it means to design a programming language. So it's one thing that happens a lot in computer science is that we build things in layers. There's some lower level, and then we build another level, and another level, and another level. Things are just a multi-layered kind of thing. It's just super complex. But that's how you can kind of tame complexity in a way, because things are structured. Okay, you know where you are in each layer. So here's an example. I added some instructions for your machine. For example, the instruction swap, that swaps the values of two memory addresses. So you can say, for example, swap 13 with 15, swaps the values of memories location 15 and 13. Okay, that's a new instruction that I added. So you can do this without, in the older version of the language, you could do that too, which is basically you fetch the value at address 1, you put it in R1, you fetch the value of address 2, you put it in R2, and then you store it the other way around, right? So you store R2 in address 1 and you store R1 in address 2. So you can do this, right? In the previous version of the language, you can do this. But because this is so boring, right, and it kind of breaks the concept of swapping. What does this mean? Well, I'm swapping the values. Oh, okay. So maybe I should just provide another instruction that just says swap, right? And how is this instruction implemented? Well, it's exactly this. Okay, this instruction boils down to doing this exactly. It's just that it's easier for us when we're writing the programs. Instead of writing these 4 instructions, we just write this 1 instruction. It's much easier for us humans, not the computer. Computer ends up doing the same work. But for us humans, it's much better to write just one line of code instead of 4. Right? And it's one line of code that has a word that actually is higher level. It encapsulates what we are doing a little better than the 4 disconnected instructions that we had in here, that in the collection, as a group, they mean swap, right? That's what they mean. But if you just read line by line, there's nothing in here that says that it's swap, right? So we have to infer it. We have to reverse engineer. Say, oh, this is swapping, okay. But if we have swap, okay, we have swap. That's what it's doing. Another example, increments, right? Incremental register. We could also increment registers before. We just, for example, add 1 to register 0, and then add register 0 with the other register, and then you increment it. Again, this is an incrementing operation, but it has 2 instructions instead of 1. And why to instruct? It's better just because we're in this next phase of algorithms that you guys are doing. We need to increment things so often. I figured that I should add something that would make it a little easier. So I added these 2 instructions. But again, these 2 instructions are just things that I put on top of what's already there. Okay, so this is how programming languages are all implemented. They are things, you can build more and more layers of what's called layers of abstraction, encapsulate concepts at a higher level, and they all are implemented, over the things that are already there, which is kind of interesting. So popular high-level programming languages, there's a gazillion. So C, Python, Java, JavaScript, C#, C++, MATLAB, etc. So people use, these are all high-level programming languages. They are not like our assembly language. There are very few people who program in assembly language. There's still some, hardware engineers, firmware engineers that sometimes need to program at the machine level. But most from the majority of programs that are done these days, they are using this higher level programming language. In fact, we will start using a higher level programming language next week, okay? Which is the language. It's not one of these popular languages. It's an obscure language that is the scripting language of this virtual world that I have been using here. So we're going starting next week, we're going to start programming these objects, and I will give you a lot of examples of how to program these objects in this other higher level language. Why so many languages, you may ask? That's a good question. To avoid human errors, to express certain things better in certain domains, for example. So there are certain languages that are good for certain, like for programming at I don't know, systems level, for databases, for example. There are certain languages that are good for databases that are not good for anything else. There are certain languages that are good for, I don't know, for reusability, for being able to use, for example, the algorithms that you already did, right? You don't want to write them again. You want to be able to use them in many ways. So there are certain languages that are very good for reusability. There are certain languages that are just different ways of people thinking about the problem. So there are object-based languages, the functional languages. So, but basically, it's to make the reason why people use for designing a new language. It's usually to make programming easier or safer in certain platforms. That's the reason that that new languages are designed. And also because it's relatively easy to create new programming languages on top of the ones that already exist. Okay, so I have a question from Giselle. In reference to part B of the project, since some of us have never used pseudocode before, could you please list the possible terms we're permitted to use in our program? The syntax. Okay, so hold on, Giselle. This is actually my last slide of the lecture slide. So let me go and explain the homework assignment. So for the part A is trivial. Part B is I'll give you already the implementation of bubble sort. You have to write the pseudocode and change a little bit, change a few things in here that aren't quite complete. And then part C is where you really have to write both the pseudocode and the code from scratch, but of course, building on what I just explained here, right? Which is the kind of the language of the pseudocode language that I have here. So, having said that, Giselle makes a very good question. Like, we don't, you guys never wrote pseudocode, and in fact, here's the thing: there is no standard language for pseudocode. All right, you may find some YouTube videos out there saying, okay, this is how you write pseudocode. Okay, that's full of baloney. All right, there's no such thing. A lot of computer scientists and those people who make some tutorials online just decided that they want to use Python for pseudocode because Python is just a really nice language for that. But it doesn't matter. The important thing are these scars, okay? So whatever language you use, whatever expressions you use for your pseudocode, try maybe to stay close to what I explained here because maybe you don't want to be too creative, but in basically you need to express five things, right? You need to express sequencing, you need to express conditionals, you need to express alternatives, maybe. You need to express repetitions, and you need to express states. All right? Those are the things. As long as you use some syntax that conveys that, I'm okay. All right? You can use, try not to use a lot of obscure symbols because then, the TA will not understand, your peers will not understand. So try to, for example, if you want to do an assignment, which this is an assignment, maybe you want to set the value of some of these, important state variables. You want to set it to a certain value. Maybe use an arrow, a left arrow, for example, which is sort of what I'm using here. For tests, the if, of course, is an important keyword. Then, otherwise, things like that. But it's, as I said, there's no standard language for pseudocode. But try to convey the five important concepts so that all pseudocode languages need to have. Okay, that's sort of how it goes. So you can stay very close to what I just said here, but it doesn't matter. Nobody's going to type, syntax check what you write. As long as whatever it is that you use that says, okay, index that gets 0. Whatever is used to say index gets 0, even if you write index gets 0, that's probably fine too. It's understandable, okay? So perhaps you may want to, if you want to deviate from from the little, the informal language that I have, semi-formal language that I have here, that's fine. Just, show it to another of your peers and ask, do you understand what I'm saying here? And if the peer doesn't understand it, maybe you should check what is it that they don't understand. Okay? Any other questions? You may, if you find yourself looking into YouTube tutorials about pseudocode, and I've seen quite a few, and the person there presents you with Python, which is basically what a lot of these tutorials use. If you want to use Python, that's fine too. I find maybe what's going to happen is that some of your peers might not be able to understand because again, it's um, perhaps a little too formal, and so that's why I'm kind of I've backed away a little bit from full Python because it's Python is actually a programming language. It's not an algorithm language. So I stepped away a little bit from it. Okay, so in this last 5 minutes, I just want to tell you a couple of things. I want to first. I want to. Which one should I tell you first? Um, the first thing I want to tell you is that where the object is that has the goodies for today's lecture, but don't stand up yet. I'll tell you where it is, but don't stand up yet because I want to show you something else before you go. So the object is this blue orb over here on either side of the stage. Just right click on it and take a copy. And inside of this object, and then you put it on your lawn, and inside there is a note card that is the program, the machine language program of the linear search 1 with one number that I just went through here in class today, okay? So this is the one that maybe you want to start with and kind of play with. So, but what I want to show you before we go is this program in action. And so I have it up here. Sorry, you guys don't know, but I have oh, actually I don't have it up here. Damn it. My home is on the other side. So hold on, let me go to my home where I have it. Let me teleport. So I just want to show you the program in action and to point you to where you should be paying attention. What's the important thing that should be paying attention? In this particular case, I find very useful that to pay attention to one particular information in memory. So let me go here, and I have the program here. All right. So this is the linear search that I went through, in class and that I understand, that I explained. And I'm going to let it run, and it's going to take a while to run. But I'm going to tell you what you should be paying attention when you are looking at the program running. Okay. To see if it's doing the right thing or the wrong thing. So I'm going to run and see the 12 numbers have been put with random numbers over here. And then I'm going to search for a number that is there. So let me search for like I don't know, 3305, okay? Okay, so I'm going to search for 3305, which is in location 0, 1, 2, 3, 4. So it's in location 4. It should find it in location 4. So let me enter it. The program's going to run. And the point that I want to point out is that you probably should be looking at this location 4. Okay, so as I said, location 15, I'm sorry, location 14. Location 15 has the number that I entered. Location 14 has the index that is being looked at right now. And so this one, it should go from 0 to 12 eventually. But I know that at index 4, something should happen, right? If I pass 4, then the program is not working correctly. Okay, so in this case, it worked correctly. But so I find it useful to be looking here at what's going on in this index, because if it passes the index where the number is, then there's something wrong. So this is just a little hint for you to kind of, as you're developing your algorithms, try to focus on the parts of the memory that are actually sort of important clues for whether the algorithm is working correctly or not. Okay? So, having said that, we can end the lecture here, and make sure to take your attendance. Okay, click the attendance button on the auditoriums, and take this little orb, the blue orb, put it on your lawn, and let's do the algorithms. Actually, you know what? I also want to ask you, but I guess we can do this in Piazza. If you guys need extra time for the algorithm, so the algorithms project is due on Sunday, but if I'm willing to extend the deadline if people want extra time, okay? So we'll have that conversation in Piazza. Okay, goodbye everybody.